I'm going to pass the torch to Judith, who's going to tell us about some work we're doing in UMass and in Canada and at Rockefeller.
All right, everybody. My name is Judith. Thank you very much for attending this session. And thank you to BINA and Katerina to allow us to present you the work we've been doing in Canada with regard to this topic. So I'll be presenting the work that we've been doing under the umbrella of Canada BioImaging with respect to research data management. My name is Judith, and I've been running a small business called Microscopy, Imaging, and Analysis for 17 years. And the founding vision of me as Cellavie was that microscopy had to be done in an artifact-free, reproducible, and quantitative manner. I used to be a core facility person at McGill University, which is based in Montreal, and I still have very close ties with the Montreal Light Microscopy Network. And of course, we're a member of Canada BioImaging. I'm also an active member of BINA, QuaRep, and more recently, I've joined the microscopy-related ISO committee, specifically in Canada. So as Katerina has mentioned earlier, the Center for Open Science hired me as Cellavie to assist them with the reproducibility project in cancer biology, and more specifically, that was replication study number 20, and that was all about preparing sample for confocal microscopy, getting on the microscope, acquiring confocal images, and doing a data analysis. And the conclusion from this study was that insufficient materials and method and metadata led to reproducibility issues. So if we consider the life cycle of imaging data from sample preparation to acquisition, image analysis, and the publication, with regard to that particular project, you can say that we were lacking 90% of the information to be able to reproduce the study that was published. But we did our best effort, and we had a good collaboration with the original author, and the results were a bit challenging. So back to research in Canada, the three agencies responsible for funding Canadian researchers are now making it mandatory to adopt research data management plans. And this means that on the third line here, that the grant recipient are required to deposit into a digital repository all the digital research data, metadata, and code that directly support the conclusions that they reach when they publish their work. And in the world of microscopy, as far as I know, the open source tool OMERO is the best option for us to adopt. So I'm going to go very briefly over this, but this is just to show that OMERO is a microscopy image database, but it actually does a lot more than just databasing images. If you deposit your raw data and carefully annotate your data, it becomes a really powerful tool to go over the existing data that's already existing in the database. You can tag and query. It can be your starting point for running your quantitative analysis, your visualization, and you can link to the data in this database important information such as the processed results of your analyses. So, hold on. Okay. So in Montreal, the Tanenbaum Open Science Institute is affiliated with the Montreal Neurological Institute, which is itself affiliated to McGill University. And TOSI funded a pilot project to foster the adoption of OMERO as an open source tool to help addressing these requirements from the funding agencies in Canada. This project was under the leadership of Claire Brown. I don't need to introduce Claire in this audience, and also Thomas Stroh, based at the Neuro. And Thomas and Claire hired Cellavie to help them go through that project. At the beginning of the project, through meetings with the various scientists in the Canadian Network of Scientific Platform, we had the opportunity to chat with members of the Canadian Astronomy Data Center. And this was very, very inspiring to learn how they've been doing things. So imagine that you're launching now a space telescope and it lives in orbit of planet Earth, so you can no longer send people on the telescope to do image acquisition. So a few decades ago, the astronomy field had to get organized so that they would acquire data set, but also establish well annotated and curated data sets so that they could be reused and or reanalyze with different tools or different hypotheses. And they actually foster this change of culture also by providing funding opportunities. And now this data set is also open to the world. The digital astronomy data live in the cloud on what is called the Digital Research Alliance of Canada. This is a large research computing infrastructures with computing clusters distributed all across Canada. Canada is a fairly large country, and these different data computing centers are all interconnected with fast internet connections. So the mission of the Digital Research Alliance of Canada is to provide support for research. And here we're talking about cloud-based research data management, cloud-based advanced research computing, and the development of research software. There's a strong emphasis on using and developing open source tool. And one member of Canada BioImaging, Steve Ogg, at the University of Alberta, installed a cloud-based instance of OMERO in 2020. And we now, Canadian scientists, have access to a cloud-based instance of OMERO that we can use for our research. Now, back to our life cycle of imaging data. Largely inspired by what the astronomy people have been doing, we came to realize that it was one thing to have access to a database, but we needed a well-annotated database and some controlled, structured and organization so that it becomes a truly a valuable database with the possibility to run queries and search the database. So this pertained really to the first step of the process and sample preparation, experimental design. What is the origin of the sample, how we describe the experiment, the date, the treatment, the conditions, the various steps in sample preparation. This is all information that is necessary if we want to truly reproduce an experiment. So we wanted to collect that information in the context of OMERO and link that information within the database where the raw data sets are living. And while getting organized to start this task, we came to realize that Katerina and our people were already doing that in Boston. So we joined force with her group to generate automated batch import of images and experimental metadata in OMERO. So essentially, we are in a case studies phase where we are working with early adopters, and that's where Thomas and Pina you heard yesterday, and we're interviewing people in their labs to understand what sort of information they need to gather with regard to experiment design, sample preparation. How do they transfer data out of the microscope and possibly onto a server, and how we're going to help them bring all this information into the national database of Canada BioImaging. So we're working in close collaboration with Alex Regano, who's a software engineer with Katerina, and we also hired Alice Kang, who's a computing science student at McGill University. Overall, what we're working on is a script combined with spreadsheet templates, which will allow us to upload experimental and sample metadata simultaneously with the microscopy raw images into OMERO. So the way this would work at the moment is we have people acquiring images on various microscope, and Alex and Katerina came up with a spreadsheet that is being constructed to capture metadata that pertains to sample preparation and experimental design. There are 3 tabs in this spreadsheet, and the first tab is about the project level metadata. Who's the investigator, what lab, what institution, and general description of the experiment that is being done. The second tab pertains to what is called dataset level metadata, and this is going deeper into the images themselves. So we have multicolor images, what's the fluorophore, the fluorochrome, the fluorescent protein that is being used, the imaging conditions, the staining conditions that pertains to each of these individual color channels. And lastly, we have a tab that connects the images that we want to upload into the database. So altogether, the spreadsheet templates will collect sample preparation metadata. Work is still in the progress to make sure that we use controlled vocabularies for capturing this information, and whenever possible, we used established ontology so that, as Katerina was saying, the ultimate goal is to be able to have this human and computer readable information. This is organized into a folder where the raw data lives along with this Excel spreadsheet, and Alex has developed a script which will upload all this information simultaneously into the OMERO database. And now we're going to have raw data and a lot of metadata associated with experiment and sample preparation. So obviously, we're using Micrometa app to capture metadata that pertains to the hardware, the microscope itself, and also the same Micrometa app to capture setting information, which is specific to the various color channels that are being imaged in the data set that corresponds to the data set. So this is the output of the script and spreadsheet template that Katerina and Alex have developed. So we have our raw data sets showing up in OMERO web up in the upper portion of the figure. And we have, because again, because of the work of Katerina and Alex, there's a Micrometa app plugin that feeds into OMERO web. And this allows us to access the Micrometa app information captured for the microscope hardware and settings. Next, if we consider one particular image, you're going to see again that through Micrometa app, by attaching the JSON file for both the microscope hardware and the settings, that both JSON files being generated by Micrometa app. Now we have access to this information within OMERO. And now the script and spreadsheet template have captured a number of key value pairs. We have key value pairs that are available at the level of the data set, and another set of key value pairs that are at the level of the project, which is a higher level information. So this is work in progress. But I wanted to, so I wanted to continue on this topic because again, the life cycle of imaging data also pertains to analysis and data visualization. And this particular example is actually one coming from the activities of me at Cellavie. We do quality control measurements on microscope. And for example, if we acquire a data set to measure the color co-registration performance of one particular confocal microscope, we've developed a workflow in NIME Analytics, again, open source software. And this is using ImageJ code to essentially start with the raw data and do all these steps. And we output an Excel spreadsheet for the results of these quality control measurements. Now, what we've been able to do now that we have access to the Canada BioImaging platform, we can now store the quality control measurements into the OMERO database, and we can link these files to both the NIME analysis workflow as well as the result of the Excel spreadsheet measurement itself. So we're getting closer to establishing a very useful microscopy metadata cycle. As you know, starting from the NBOQ microscopy metadata extension, we can collect information regarding the hardware and the acquisition settings through the use of Micrometa app, which generate JSON file for both hardware and acquisition settings. We're working to automate the upload of this information along with information regarding to experiment and sample preparation. And now this now can live in the OMERO-based server on the Canadian computing infrastructure, and we have access to all this information. Yet again, if we use the MethodsJ tool developed by Claire Brown's lab, out of this we can generate fully detailed materials and methods which will be useful for publication. And we also have access to detailed information from the microscope, and that can include quality control measurements. And we can also link this to precise image analysis protocols. So in the end, we have the capacity now to further complete our image data image. I'm running out of my words now. The imaging data lifecycle of data. So this is still work in progress, and we would love to entertain and work with you if you want to contribute to further development of this of these tools. Thank you.